I don't think I thanked people on the ground organising this conference so elegantly. Many thanks. Khalil, Cham Cham in particular, Chris Doog as well. Many thanks. Okay, so so part 2, probability and the multiverse, an Everettian view. I'm going to be focusing on probability, of course, but let me just summarise where we got to yesterday. And here's a very succinct way of putting it all together, due to E.T. Jaynes. Our present quantum mechanical theory, if left out, is a peculiar mixture describing in part realities of nature, in part incomplete human information about nature, all scrambled up by Heisenberg and Bohr into an omelette that nobody has seen how to unscramble. Yet we think that the unscrambling is a prerequisite for any further advance in basic physical theory. For if we cannot separate the subjective and objective aspects of the formalism, we cannot know what we are talking about. It is just that simple. I think that is pretty accurate. Whether unscrambling the omelette is a prerequisite for further advance is more of an open question. I myself am rather agnostic on that one. But certainly the omelette needs unscrambling. I went some way, I hope, in my talk yesterday in the objective side of the quantum state as representational, as descriptive. But then there's the other Janus-faced side of the quantum state, which is its role in dictating or controlling probabilities. Yesterday I was philosophically prosaic. I had my 3 pillars, and those 3 pillars, I hope you will agree, I'll not put them up again, were rather innocuous. A general principle of functionalism applies across the sciences, what I called Galileo's dictum. If you're interested in questions of observation or how we obtain knowledge in a physical context, then model the observer in the physics. And what I'm calling McIntyre's principle, that objects, mostly on close investigation, turn out to be processes. Okay, so I could be prosaic, I think, because, and keep philosophy out of it, keep metaphysics out of it, but when we come on to probability, that just isn't true anymore. And it's true because probability is inherently connected to a large number of philosophical topics and has been investigated by philosophers for quite a long time in relationship to those topics. So of the ones I've got here surrounding probability, time is perhaps the least essential one, but I'm going to leverage off that in keeping with my remarks yesterday, that an understanding of how we deal with temporality is helpful, it gives useful guidance in quantum theory. But the others, language, mind, measurement, and identity, are all absolutely central to probability. Of these, measurement has figured less in philosophical discussions, but of course is much more prominent in physics. So I will say quite a bit about measurement, but I'll explain the links to language, identity, and mind as I go along. Okay. Well, I should preface everything now that follows with this remark, which is really echoing something that Max said yesterday. The Everett interpretation of quantum mechanics seems to bring with it extraordinary conceptual problems or questions. And actually those extraordinary conceptual problems and questions are pretty well present anyway in modern science. I echo that. I think that's correct. I think that's right. And it's especially true of probability. What I think the Everett interpretation does is it brings every difficult concept, characteristic of probability to the fore very starkly and presents it in a way where it seems the question is really rather urgent. Okay, so I think that's what's going on. There may be 1 or 2 things that are special to Everettian quantum theory. We'll be in a better position to say at the end of this talk. The first and most immediate pressing problem, of course, is look, if according to the Everett interpretation, in some sense, everything happens, all possible outcomes are somehow real, then how can we make any sense of probability? So there's a very blanket question about the nature of probability in this context. And more specifically, one can ask, supposing one knows everything there is to know about the branching structure of the quantum state, in what sense is there any uncertainty? One can ask, is a notion of objective probability available? If so, what in the world corresponds to those quantitative chances? If there are objective chances as physical quantities or structures in the world, why should we conform our beliefs, degrees of belief, about the relevant circumstances to those quantities? If there are no physical chances but only degrees of belief, what in the world constrains those beliefs? And last and not least, in what sense is the theory testable? And in particular, is the theory testable by someone who does not believe or does not yet believe that the multiverse has the branching structure that Everettian quantum theory says it has, who doesn't, as it were, buy into any of the claims of the theory? Right, so this is a bunch of questions that any philosopher really is going to ask about the Everett interpretation. But, and this is the punchline really, they will also ask, philosophers will also ask the same questions, forget about the first one, the same questions about any physical theory in which there is a notion of probability as something objective in the world. I mean, briefly, philosophers have found it extraordinarily puzzling how there could be anything objective in the world that plays the role that objective chance seems it had better play. And the way that physicists get away with this, and a lot of people, most of us get away with it when we're not doing philosophy or philosophy of probability, is to be crude frequentists, simply to identify probabilities as relative frequencies, as objective things out there in the world. The problem with frequentism is it doesn't work. Okay, I'm not going to go into the background to that or the arguments as to why frequentism doesn't work. It just doesn't hold up to inspection. So, what do you do when you give up on frequentism? All right, so I'm going to address these questions more or less in order. But before I do so, I do need a bit of mathematical apparatus in order to be more careful in how to describe this branching structure of the quantum state. So in a word, what I need is the decoherent hysteresis formalism. It's particularly useful, simple, intuitive. It gives a space-time representation of the quantum state. So think of the quantum state unitarily evolving in space-time, and think of what is the structure of that object. Okay, that's usefully provided by the quantum hysteresis formalism. And what that formalism does is essentially, it's a bit like a lattice. It sticks the quantum state onto a lattice. It discretizes time. It discretizes or coarse grains phase space. It takes von Neumann's building blocks of reality, and it constructs sequences of such projections acting on the state, and then the superposition of such sequences gives you back the total state. Okay, so let me just go through that. I'll be fairly quick, and if you find it puzzling, I'm sorry, I do need some schematic tools to discuss probability more accurately. So start off with phase space. So here we've got a coarse graining upon it. So think of Gaussians, sharply peaked, localized in position of momentum, and then integrate them over some region of phase space, and you'll get out a projection. Define Heisenberg picture projection operators. Okay, I'm sorry about a sign problem with this. Anyway, it should be e to the minus ht on the right. So what is happening here is what this projector is doing, acting on the state in the Heisenberg picture. The state is something that doesn't change with time. We can think of it as the state at time zero. It could be the state at the origin of the universe if we want. So e to the iht is going to unitarily evolve that state forward to time t. The projection p alpha k is then going to act on the state. The state can be represented as a superposition of a part which is an eigenstate of p alpha k and a part which is orthogonal to that. So the part that is an eigenstate of P alpha k is what is retained, and then that state is taken back again to t equals 0. Okay. So a history is going to be a sequence of such projections. This is normal notation for it, often called chain operators. So C subscript alpha. Alpha is a sequence of configuration cells in phase space. Okay, and now put out of your mind Everettian quantum theory. Just pretend that you're doing something like, I won't call it Copenhagen quantum mechanics. Max, I know, called Copenhagen quantum mechanics what Bohr was doing. I think Bohr was doing something rather different. I'm calling Copenhagen what Bohr was doing. So let me just call it the conventional projection, the conventional measurement postulates. So in accordance with those conventional projection postulates, measurement postulates, what one would say this quantity is, this mod squared of this C alpha hitting the state, is going to be the probability of that history, where we can think of that history as developing through a sequence of measurements, each of them projective, each of them invoking the projection postulate, hitting the state with a projection operator. What is left is then, if you repeat the experiment, you'll get the same state. Then time evolve forward, hit it again with a projection operator onto another cell in phase space. Again, unitarily evolve it forward again. We have this discretization of time. When you look at the modular square of this thing, you're just getting the total probability for that history to evolve under that sequence of measurements. Okay, and you can define relative probabilities, the probability of a history, a concatenation of alpha and beta, so a sequence of regions of phase space. The beta is listing those, alpha, subsequent regions of phase space, then divide by the modular square of the component of the state corresponding to beta, the relative probability of the history alpha given beta. Okay. All right, now the way this was developed back in the 90s, even earlier in the late 80s, with the people like Bob Griffiths and Roland Omne and Gelman and Hartle. So the certain consistency condition is put into place. I'm calling it consistency, different terminologies were used. Gelman and Hartle called it decoherence. So orthogonality of these vectors corresponding to histories that differ if only in one event along the sequence of events represented by these projection operators. It's a non-trivial condition. It depends on what projections you use as to whether it's satisfied. And in particular, if you look at the two-slit experiment, there it isn't satisfied. And in the case of the two-slit experiment, if you try to represent each of these histories, projection operator onto, say, a source particle at alpha I, what I've got there written as alpha I for initial. If you have projection operator onto region of phase space corresponding to the particle being at alpha 1, a second region of phase space corresponding to the particle being located at alpha 2 with appropriate momentum spread. And then finally, projection operator corresponding to the particle arriving at the screen. So if you set up those histories and you calculate the probabilities of those histories, then it's simply not the case that the consistency condition is satisfied, which is exactly corresponding to the fact that we have interference between the histories. So this consistency condition, we can understand it as a condition on non-interference of histories. Okay, and of course in this two-slit experiment, as Feynman famously said, is contained, well, according to Feynman, all of the mystery of quantum theory. I don't think that's quite right, but a good part of it. Okay, so more terminology. A consistent, or also called a decoherent history space, is going to be, at each time, we're going to have a resolution of the identity, the set of projections corresponding to regions of phase space, exhaustively mapping out the phase space. And the set of all such histories is then a decoherent history space. And if it's consistent anyway, we then have a measure on that space of histories which satisfies these nice sum conditions. Okay, so all of that is not enough for the kinds of purposes we want. The general picture that I was putting in place yesterday, all of that is not enough. The consistency condition itself is much too weak. We have non-interference of histories, but we don't have anything like emergent, dynamically robust, autonomous structures propagating as patterns through the state, to put it into that phrasing. That is precisely what is given by quasi-classical domain in Gelman and Hartel's terminology. So it's a consistent history space with a state sharply peaked on histories obeying approximately classical equations. Okay, so that's the thing that becomes relevant to an Everettian interpretation of quantum theory, insofar as we can find such a history space, a quasi-classical domain, such that the histories in that space correspond to propagating patterns, if you like, obeying approximately classical equations. Okay, I'm giving you now just a quotation from Jonathan Halliwell, who's pretty neutral on interpretational questions, one of the more careful and systematic investigators of the decoherent histories formalism. So I'm giving the quotation partly to illustrate the technical developments that have been made, and partly to illustrate a certain worry that one might have. Okay, so first the technical developments. This is the final picture that we have. Halliwell in particular was here working with a model where what was giving consistency, but actually also giving the equations running along the histories, is hydrodynamical variables, where you're integrating local densities, which are approximately conserved. And it's by virtue of being approximately conserved that the equations for each history are approximately deterministic. Okay, so on this model, it's a sort of hydrodynamic model. We can imagine an initial state for the system which contains superpositions of macroscopically very distinct states. Decoherence of histories indicates that these states may be treated separately, and we thus obtain a set of trajectories which may be regarded as exclusive alternatives, each occurring with some probability. Those probabilities are peaked about the average values of the local densities. We have argued that each local density eigenstate may then tend to local equilibrium, and a set of hydrodynamic equations for the average values of the local densities then follows. We thus obtain a statistical ensemble of trajectories, each of which obeys hydrodynamic equations. These equations can be very different from one trajectory to the next, having, for example, significantly different values of temperature. In the most general case, they could even be in different phases, for example, one a gas, one a liquid. Okay, and this is the sort of messy complexity that you get into as soon as you back away from the highly idealized and carefully fabricated von Neumann type measurement process. If put experiments out of the picture altogether, Everett interpretation's got nothing special to do with experiments. Experiments is just one physical process among others, very special ones, as I say, very carefully choreographed ones. But in general, this is the sort of situation, at least in the hydrodynamical case. All right, and there are many other models, typically models, linear models, couplings to oscillators and so forth, models of Brownian motion, heat baths quite generally, in which you get out the sorts of equations that you would expect governing the various histories involved. Okay, but look at the red sort of comments. Those are the scare quotes, really. So what do we mean by average value here? Isn't that bringing in probability? So there's a worry. There's a worry that in performing this sort of analysis, in the kinds of operations that one makes, taking expectation values, taking the partial trace, and so forth, is that not smuggling in a probabilistic interpretation of the theory? Okay, so that concern, I think, is a perfectly reasonable one. I'm not immediately going to lay it to rest. I think it's one that needs to be, attacked, really. But you need the big picture in order to see what's going on. I would just say this much, though, that, I mean, really, if one's taking, first of all, let me just make a comment about coarse graining. So if I take by alpha bar, what I mean is a parameterization of a sequence of cells in phase space, and I can choose a coarser graining on phase space. And if I look at C alpha for contained within that coarser graining, so I'm going from a fine graining on phase space to a coarser graining, then I have a simple relationship of this form. If I look at the probabilities of histories alpha, I can also consider the probability of the coarser grained history, and if I can write it in this form, that's the consistency condition. So, in a certain sense, what's going on with the decoherent history space or consistent histories formalism and the consistency condition is a very nice, very natural formalism for coarse graining, fine graining, in a way that preserves simple additive relations of these forms. And what I mean by P probability at this point is no more than a number, numerical values that are attached to histories which have yet to be interpreted as probabilities. And what I mean by a partial trace is a certain kind of coarse graining, where I integrate out over certain variables, retain others, a certain kind of coarse graining. Okay, so none of those concepts, I think, need involve probability. That's the essential claim. Right, well, if we can at least run with that, going back to my little constellation of topics surrounding probability, what I'm replacing the dice by is this branching structure. And this branching structure, we can imagine it as just consisting of these sequences of projection operators, these chain operators, acting on the state. So C alpha acting on Heisenberg picture state is going to return, I can write it subscript alpha if I like. This is going to be the quantum state from a formal point of view of the quantum state, but it is encoding all of this structure, okay, corresponding to a history which could be from Big Bang right up to the present, with the condition that these vectors are orthogonal to one another where alpha, when the alphas are different, when the histories differ in any respect. And then it should be clear, it is not already obvious, that if I sum over alpha, C alpha, psi, of course, I just get back psi. Because summing over all C alphas, I'm just summing over projection operators. I can do it sequentially, starting from the latest projection operators, sum over all of those, get unity, then go to the time before, sum over those, get unity, and work my way through all of these sequences. I'll just get back the original state. So from an Everettian point of view, we just have the total superposition of these histories, of these vectors, each representing histories. And I'm just giving that a nice, I hope it's nice, graphical illustration there. 3 histories I've got. But look, here's one of the big differences with the appeal to von Neumann measurement processes and the analysis of worlds as corresponding to measurement outcomes. In no sense are there as many worlds produced in measurements as there are distinct outcomes. Okay, so that's an inappropriate model. I mean, what we're looking at here, these histories are corresponding, as I say, to regions of phase space. These regions of phase space will, just very smallest molecule displaced by a nanometer or two sitting on the edge of the apparatus. That's going to do to give a distinct history from one where that molecule, which may have nothing to do with the experiment, is not so displaced. Okay, so what is really going on all the time, and what is going on in measurement as well, is a branching structure involving countlessly many different histories. Perhaps infinitely many. Okay, it would be a countable infinity if so, but perhaps even infinitely many. So the question of what is the number of branches produced on performing a measurement is poorly defined. One can make it sharply defined in terms of the specific coarse graining one puts on phase space. But that's clearly an artifact of, as it were, putting quantum mechanics on a lattice, right? Okay, so let me just start off. I want to just cover 2 or 3 of the philosophical topics. I don't want to spend much time on them. I think most of the interest is with measurement. The nature of this conference is really directed to cosmology, and I will conclude with I think one of the things that results from Everettian quantum theory vis-a-vis probability is a critical stance on the way that the concept of probability is being used in cosmology. So that will be what I'm heading for, what I'm going to try to conclude with. But along the way, I think I've got to say a bit about these philosophical topics. So I'll start off with time. Time, identity, and language are all related, really, in the question of how do we make sense of probability at all? All right, so I go back to the block universe and what I had up yesterday, and I think what is a spectacularly mistaken, bad thing to say about the space-time representation or the block universe that we see there due to Weil. Here's more bad things that you can say about space-time as a structure with world lines running through it. You can conclude, well, there's no change. The notions past, present, and future have no meaning. There is no becoming. There is no free will. One can do that. And many philosophers have done that. They throw up their hands at this kind of representation and say the physics is somehow inappropriate, or we've got a mistaken take on the physics. One of the reasons that I was attracted to the Everett interpretation, may I say, speaking as a philosopher, I thought it's a philosopher's job to take physics and use it to impact on philosophy rather than take philosophy and try to use it to impact on physics. The basic reason being I think physics has done better than philosophy. So, you know, those who push for hidden variables, those who push for dynamical collapse theories are really saying, look, we know a priori, or we know on the basis of antecedent intuition or pre-theoretic knowledge somehow that the world has to be in a certain format, certain kind of picture must be appropriate, and therefore the physics must conform to it. And I'm doing the opposite. I'm saying let's take the physics and see how it impacts on philosophy. And here's an example. Don't insist on some pre-theoretic understanding of time and use it to presumably dictate that there's something wrong with relativity. Do the opposite. Assume space-time relativistic four-dimensional perspective is entirely acceptable, is physically fruitful, has proven its worth, and instead try to figure out what the right thing to say is. And here are some right things to say. Change consists of relations among events throughout your lifeline. Past, present, and future is, becoming is, free will is. One's going to give stories about those things. And here's a simple story to say about tense. What is the meaning of tense, past, present, and future, given this four-dimensional perspective? Answer, something that philosophers often do, to give content, give truth conditions for statements. So the statement that E will happen, uttered at S, is true if E happens later than S. So pretty straightforward, you know, quite unsurprising, prosaic really. But now let's go to the branching universe. And again, you can conclude something similar. There is no probability. There is no such thing as uncertainty. There's nothing about which to be ignorant. So somehow Everettian quantum theory has to be abandoned. That would be the implication. And if that means abandoning quantum mechanics as standardly formulated, then so be it. So this is the sort of move I'm resisting. Instead, let's look for something informative to say if the universe does have this branching structure. And then one's going to say this. Probabilistic events are branchings, and probabilities are relative weights of branches. And then one's going to tell a story about uncertainty, a story about ignorance. And of course, temporality is all mixed up in this. So we're going to have to lean on what we've understood already in the deterministic four-dimensional case without branching. Okay, so here's how to give an account of uncertainty. So truth conditions for E is uncertain, uttered by A in WK, is that A at S does not know which world is A's. Or putting it another way, as of S, in some branches E happens, in other branches it doesn't happen. So for that reason, therefore, E is uncertain. And that can be parlayed up into a characterization of what we mean by a person or thing, because of course physics doesn't really dictate how we use ordinary words. So here's how we can use the word person or thing. We mean a branch part, a part of a branch, an ordered pair, person branch or thing branch. And here I've given the denotation for it. And if that's what a thing is, if that's what an event is, his beta is describing some local event, or it could be describing a person, or perhaps a stage in a person's life. So it's up to us to find an appropriate way of translating ordinary words into, or giving truth conditions for ordinary sentence in terms of the underlying physics. And this is a way that works just fine. Well, I've called this branching worlds, and by branching I mean to be neutral about metaphysical ideas as to how one's supposed to be thinking about possible worlds. Here's how philosophers tend to cash out, be explicit about the notion of possible worlds. Possible world semantics has proved extremely valuable in philosophy, mostly for dealing with modal questions, questions of possibility, necessity, and so forth, counterfactuals. So philosophers like to use possible world semantics. It's a formal system whereby one quantifies over possible worlds. And then the question arises, well, how is one supposed to think about these possible worlds? The extreme, very few people believe it, the extreme view is that they actually exist. The more standard and prosaic view is that, well, no, they're not possible worlds like this world. They're linguistic entities or something else. But still the question arises, how are we to think of their parts? This is how metaphysicians think. And here's one way of thinking about it, that these worlds overlap. So, meaning that their parts at this early time, I've given it by S, are numerically shared by these different worlds. Don't worry if you don't understand what this means, by the way. That's fine, really. It doesn't really, I mean, it doesn't really mean anything in application to real physics. Because, you know, what are we supposed to think of parts of a dynamical process after all, right? Or, well, I can say more in this vein, but let me just move on. Here's another way of thinking about these possible worlds, that they diverge. So they don't share parts that are numerically the same, they're just qualitatively the same. Okay, and of course, if the picture is diverging worlds, then very simply what uncertainty consists in is, I don't know which world is mine. We don't know which world we're in. If you have the picture of overlapping worlds, then you might think, well, we're in all of the worlds that have the qualitative character that here in this room that we have. And then you might think, well, in what sense am I in one world rather than another? And then in what sense is there any meaning to the notion of uncertainty as to which world's one in? So you can see how this goes. I don't think, in fact, I'm quite certain that this matter is dictated by the mathematical structure of quantum theory. I've given a formal model where this makes sense. I've given another formal model where this makes sense. And it's really up to us as to which one we choose to best make sense of our ordinary lives in the light of the physics. Okay. All right, so I hope to have given you some idea how time, questions of identity, questions of language kick in. Let me talk now about probability and the measurement of probability. I've got handsome is as handsome does up there. That's a nod to Dennett's quote. It's a question of functionalism. The idea is this. We are going to identify branching events and branch amplitudes, norm squareds of branch amplitudes and ratios in those things as objective probabilities because they behave just like objective probabilities. Okay? And in particular, they're measured just like objective probabilities. And the beauty of the Everettian framework, and I don't think this is true of any other approach I've come across in quantum theory, is that once you've identified what objective chance is, namely chance events or branching events, values of chance on the norm squared ratios and norm squared of the branches involved, once you've identified what those objective chances are, you can then ask, well, how on earth can I measure them? How can those values of those amplitude squareds be registered at the macroscopic level? And that's a purely dynamical question. Just, play around with the equations, try to figure out what sort of unitary interaction could there be that drives, if you like, transports amplitude squares onto something that a device can register at the macroscopic level. What kind of unitary evolution can do that? And how? So how can probability be measured? And look, here's a bunch of facts about probabilities that we all know, but now we can explain them. Here's one thing we know. We know we never measure absolute probability. Absolute probability for the universe, we know we never do that. We know that we never measure single case relative probability. When I say relative probability, I mean of one event rather than another event happening. So we just can't do that. Single case probability, we can't measure it. If we could measure it, we could signal faster than light and do all sorts of other things. We all know that there is no probability meter that can measure relative probabilities on repeated trials with probability 1. We know that too. You just can't do it. Throw a dice 20 times and you measure the relative frequency, but it is not the case that with certainty that relative frequency is the probability of the dice landing one way or rather than the other. Why not? Why can't we do it? Why are there no probability measures like that? And we know there's no liquid luck, Harry Potter fans. What a shame, there's a wonderful elixir that you drink it and then you have luck. There's no good luck charms. Why not? Now, none of these questions have a serious answer on any other physical theory that I know of. Somehow it's just definitional of what probability is. I'm reminded of opium and its dormitive virtues. Okay, so how does it go with Everettian theory? I won't spend long on this, but I'll just spend a bit. So take this one. Why is there no probability meter that can measure single case relative probability with probability equal to 1? Well, suppose you've got the apparatus is W. I could take the configuration, one of these things, with the projections onto regions of phase space for the entire universe if I want. But let's just keep it simple. So here we've got an apparatus with state W. It's really meant to be an omega actually. And the microscopic system, suppose it's in the state phi c. It's a superposition of two terms. And we're interested in, can we measure C? Can we measure it with probability 1? And that means, can we unitarily drive the measuring apparatus so that it registers the value C, or C squared? Okay, so let that configuration of the apparatus in which it does register the amplitude C, so it displays it on some display, be this thing, projection, and I've got subscript alpha C. We're looking at the Heisenberg picture. It's timed. It's got a time date to it. So it's this thing. And if there were such a probability meter, then we would require a unitary evolution. Well, of course, we only have unitary evolutions in the Everettian theory, such that the initial state of the apparatus and the microscopic system we're interested in is driven to the capital UT is just to give me a Schrödinger picture state. It's more familiar. That's what that first UT is giving. But look what the rest of it is. It's an eigenstate of P subscript alpha C. Okay, that's what we want. And what happens to phi subscript C, the microscopic system? It may have been destroyed in the measurement. I'm not making any assumptions about that at all. That's getting acted on by the unitary time evolution contained in the Heisenberg picture projection, the P subscript alpha C. Okay, so that's what we'd want, the right-hand side. But if this thing is going to function in this way, then for some other superposition, phi C primed here, we'd want a similar unitarily deterministically driven outcome with a device registering C primed. But now look at those two equations. It's clear they can't be satisfied by any unitary evolution. Why not? Because the inner product of the right-hand sides has got to be 0. These are macroscopically distinct outcomes. But the inner product of the left-hand sides could be as close to 1 as I like. Okay, C prime could differ very little from C. So there can't be anything like that. Okay, and you can go through the list, put it up again. And there's more things. There's more things to this list than I've done. And you can figure out how come there can be no such probability meter. But then, of course, the interesting question is, well, how do you measure? How on earth do you measure probabilities? And here's how you measure them. There are probability meters that measure probabilities on repeated trials with probability close to 1. And what that means is you can unitarily drive a branch so that it registers the relative amplitude squared, what we were just looking at, the c squared and 1 minus c squared, on branches with high amplitude, and fails to do that on branches with low amplitude. So you take all of the branches that result, all of those with the right relative frequencies have total amplitude squared 1 minus epsilon. All of those with the wrong frequencies have amplitude epsilon, amplitude squared epsilon, where epsilon goes very quickly to 0 with the number of trials. Okay, so that's how you do it. I've just got some equations to go through here to show you how this works, but I think probably I'm a bit short of time. If we're going to have some discussion anyway, I think perhaps we are. I mean, I can come back to this, but the basic idea, you're going to get a vast superposition of states. I've got, say, n's microscopic systems all prepared in the same initial state, a superposition of phi plus and phi minus. The measuring device is going to measure in that basis, phi plus or phi minus. As a result, it's going to end up in a vast superposition of states of this form. The f here is, f here is a function mapping, telling me what are the various outcomes, plus or minus 1. So the first microscopic system, if the outcome is plus 1, then f of 1 is 1. If the second system, the outcome is minus 1, then f of 2 is minus 1, and so forth. So there'll be a large superposition of such states. Those with the same relative frequency, m over n of outcomes, would all have the same norm. And this is what I've written here. Okay, and of course that condition that they all have the same relative frequency just means that this must be satisfied. All of those minuses, I've got m plus 1s, and then I've got n minus m minus 1s. And you subtract them off, you get that quantity. And so this is the unitary evolution. We end up with this thing on the right-hand side. And if you look at what this thing on the right-hand side is, the furthest right, the summation there, it's over all of the f's with the same relative frequency. And you get this combinatorial expression involving the n factorial expression, how many different ways of selecting m out of n, okay, independently and so forth. And this thing gives you this function x of m, which I've written down in full. And the point about that function is it's highly peaked, sharply peaked, over m as equal to the ratio m over n as equal to mod c squared. Okay, so that's the crucial and only way so far that we know of how to measure probability under this unitary evolution. It's also the only way that we know how to measure probability just forgetting about the Everett interpretation, just doing physics with quantum mechanics, Copenhagen, or conventional formalism, whatever. It's how you measure probabilities in pilot wave theory in equilibrium. An interesting question as to whether you might be able to do it differently in out of equilibrium, and so forth. Okay, so enough on that, enough on measurement. I'm going to conclude shortly, but let me just come to mind. And what's going on there, the issue there is, well, coming back to my list, why should we conform our degrees of belief to these objective physical quantities? Who cares what these amplitudes squared are? Okay, I've got a way to measure them. Okay, there's branching. Okay, there's some uncertainty. But why should I bet on those outcomes, lining up my bets with the modulus squared? Why should the Born rule dictate what my subjective degrees of belief, my subjective expectations, how I'm prepared to bet, and so forth? Why on earth should that be? And this has been a really hard problem for philosophers. Okay, David Lewis is one of several, but perhaps the most articulate. He gave the general principle that subjective degrees of belief ought to conform to objective chance, whatever objective chance is. He called it the principle. And it's this: assume we have a number x, proposition A time t, rational agent whose evidence is entirely about times up to and including t, and a proposition E that A is about times up to and including t, and B entails that the chance of A at t is x. In such a case, the agent's credence in A given E is x. And really the point is it ought to be x. This is the normative principle. We ought to conform our subjective degrees of belief to these objective quantities. But why? I mean, it's, as soon as you start to think about it in that way, it becomes really rather peculiar. If you think that the objective quantities are relative frequencies, actually recorded relative frequencies, then it sort of starts to be, you can sort of maybe see why. But we're certainly not in that ballpark, are we? And anyway, we know relative frequencies don't work, frequentism doesn't work. I mean, let me just read out what Lewis has said about this. It's rather nicely put. The distinctive thing about chances is their place in the principal, which compellingly demands that we conform our credences about outcomes to our credences about their chances. Roughly, he who is certain the coin is fair must give equal credence to heads and tails. I can see dimly how it might be rational to conform my credences about outcomes to my credences about history, symmetries, and frequencies. I haven't the faintest notion how it might be rational to conform my credences about outcomes to my credences about some mysterious things called potentialities, for example. Lewis actually used the word unhumian magnitudes. That's a sort of technical term in philosophy. A magnitude that is sort of funny. It's like a power or a disposition or a potentiality. It's, you know, the sorts of quantities that aren't funny, aren't peculiar, things like mass, lengths, durations, time intervals, charge, categorical properties of things. But what a potentiality is, heaven only knows. Again, I come back to opium has a dormative virtue. Is this really explanatory? So he says, don't try to take the mystery away by saying that this unhuman magnitude is none other than chance. I say that I haven't the faintest notion how an unhuman magnitude can possibly do what it must do to deserve that name, namely fit into the principle about rationality of credences. So don't just stipulate that it bears that name. Don't say, here's chance, now is it Humean or not? Ask, is there any way that any Humean magnitude could fill the chance role? Is there any way that an unhuman magnitude could either actually? And what I fear is the answer is no, both times. So for Lewis, this was really a serious problem in his general project of analyzing things like mentality, intentionality, causation, many other counterfactuals, many other philosophical notions on this Humean tapestry of events, as he called it. Okay, so that's the situation. It's been in a sort of a quagmire now for decades. Nobody really knows how to make much progress with the principle. There is a project, a sort of broadly Lewisian project that I'm not going to discuss it. It's not perhaps entirely hopeless. But here's something really remarkable. This is due to David Deutsch and David Wallace. And it's an analysis of how rational agents should behave in the Everett interpretation, in the face of branching. How they should behave. There's quite a long background to this, and I'm not going to go into the details. I just want to give you just a very crude idea of how it works. It goes like this. Start off with a program that goes back to Ramsey and De Finetti and Savage. This is from the 1920s right through to the late 50s and on. And Everett himself, by the way, might have worked on this program had he not been essentially unable to get a job in the academy because his ideas were deemed too crazy. Everett was very interested in decision theory. Anyway, so there's a general program which says that actors who order their preferences in accordance with principles of rationality, order their preferences in terms of what acts do they wish to perform, where the acts are going to have certain results, certain rewards. It's up to the agents as to what reward, how they value those rewards. But initially anyway, let's suppose that these are actions in the face of uncertainty. If you obey these decision theoretic rules, then whether you know it or not, you must rank order your actions in terms of their expected utilities, where the expectation value is determined by your subjective degrees of belief. Whether you know it or not, whether you admit it or not, whether you actually figure out what one's individual subjective degrees of belief are, if you satisfy these axioms of decision theory in rank ordering your preferences, this is in effect what will happen. It's a representation theorem that says they will be ordered by expected utilities. So that's well established. It's been known for 30 or 40 years. It's quite an achievement from a philosophical point of view. But what Deutsch and Wallace showed is that if the agent knows that the branching structure is whatever it is, with the amplitudes being whatever they are, obeying those rational axioms in ordering their preferences, it's not just that those preferences are ordered by expected utilities in accordance with some subjective degrees of belief, they're going to be ordered by the Born rule. In other words, that subjective degrees of belief implicit in their activity as rational actors will be the Born rule. Right, well look, my time is up. I wanted to give a bit of an idea as to how that argument went, but I think I really have to pass it by. It's a certain symmetry argument. It's not, as far as I know, available in any other theory, partly because both outcomes are actualized. You do have the superposition of the two outcomes and therefore can perform a symmetry transformation. I will have to pass that by. Okay, and here's an example of what those axioms of rationality look like. Right, the upshot, I'm going to finish now. The upshot of all of this is I think probability is in better shape in Everettian quantum theory than in any other physical theory. It's, I think, virtually entirely understood. I mean, there's just no sort of gap left with a possible quibble about uncertainty issues, overlap versus divergence, those sorts of issues. So a great success story. But look at what it implies. It implies that there is no meaning to objective probability other than that produced by branching. And branching never happens except through decoherence. So objective probability only has meaning insofar as you have decoherence. And I think that is a lesson that's rather important for a lot of uses of the notion of probability, among other things in cosmology. For example, in the idea of fluctuations in the vacuum. Okay. And of course, one of the standard ways of explaining why is it that we have the enormous problem that we do, it seems, with the cosmological constant, it's because there are these fluctuations in the vacuum and they become larger and larger the shorter the length scales, going to infinity, in fact, unless new physics kicks in. And this gives you the number of 10 to the 120 or whatever, assuming new physics kicks in at the Planck scale. So the zero-point energy goes all the way down. And that's just wrong from an Everettian point of view, if what you're talking about are probabilistic fluctuations. Now, it may well be, and I think it is the case, that the cosmological constant problem is not analyzed as due to statistical fluctuations, stochastic fluctuations in the vacuum. That's just a mistake. Okay, but that doesn't mean that there aren't fluctuations in the vacuum. There are, but they only occur up to decoherence timescales. The measured value of dark energy, the frequency is 10 to the 12 hertz. If fluctuations in the vacuum, because of decoherence, are controlled by the thermal background, the microwave background temperature, then they should be around 10 to the 10 hertz for each quantum field. So there's some coincidence there. I'm very wary of suggesting that as a serious avenue to explore, but it's an illustration of how don't think there's anything probabilistically fluctuating in the vacuum unless there's decoherence going on in the vacuum. Insofar as there is decoherence going on in the vacuum, there is statistical stuff there, and we can appeal to things like fluctuation dissipation theorems within probabilistic statistical physics. Okay, so I'll end with that. Thank you very much.